Welcome to IT 533 Data Mining. My name is Sonja Struber. I am your instructor, and this is the second part of our conversation on recommender systems. We will discuss explicit and implicit ratings and their accuracy. We will also discuss user-based filtering and item-based filtering, and one of my favorite topics, cosine similarity. We will then discuss the Slope 1 algorithm and its implementation in Python and the MovieLens data. Implicit and explicit ratings. Explicit ratings are those where the user themselves rates the item purchased or seen, such as ratings of 4 stars out of 5 or emojis on, say, Facebook, or thumbs up, thumbs down in various applications. Whereas implicit ratings are not specifically given by the user, but rather observed, such as user clicks on a website, in-clicks and out-clicks, the length of stay on a web page, the shares of a contribution, say on Facebook, for example, and also users' buying behavior. Now take a look at the case study in the bubble and ask yourself which one is more accurate, explicit ratings or implicit ratings. The problems with explicit ratings is that people are lazy and don't rate items, as we've seen in our previous exercises, that people may lie or give only partial information, or that people just don't update their ratings when they change their mind about items. And implicit ratings also have their problems, though, because the consumer profile that you see in the bubble, for example, can be upset if you buy presents for someone else, for example, or if someone else uses your login and your profile. This is where two different filtering approaches come into play. So far, we have been doing user-based filtering, which means that we are comparing a user with every other user to find the closest matches. The problem with that is scalability. Many applications have a lot of users, so the computation increases exponentially. And also, we most likely have sparse data in most recommendation systems that are explicit or user-based. But what if we use item-based filtering? So, for example, such an item-based filtering algorithm might find that one album is very similar to another album, and that if a user rates album number 1 very highly, we could recommend a similar album number 2 to that very user. That would be item-based filtering. In other words, in item-based filtering, we find the most similar items ahead of time, and we combine that with the user's rating of items to generate a recommendation. And similar is, in fact, the key word here. In many commercial applications, cosine similarity is used to determine how similar 2 or 3 or more items are. So let's take a look at this. Cosine similarity is defined as the dot product of, in this case, 2 items divided by the square root of one item multiplied by the square root of another item. So, for example, let's take 2 people, Alice and Bob. They each have rated coffee, tea, and orange juice. Now we want to determine how similar Alice and Bob's tastes are. So the first thing we have to compute is the dot product of their ratings for coffee, tea, and orange juice each. So the dot product is 5 times 2 plus 3 times 4 plus 1 times 5. That equals 27. And now we have the numerator here. And then we're going to calculate the denominator, which is the square root of A times the square root of B. So 5 times 5 plus 3 times 3 plus 1 times 1, and then the square root of that. That equals 5.92. And the square root of B, calculated similarly, is 25, and the square root of that is 5. So now we're going to put everything together in this formula, and we're going to determine the cosine similarity of A and B, which is 27 divided by the product of 5.92 times 5, which is 0.91. And if we plug that into a regular angle calculator, we will end up with an angle of 24 degrees, which will tell us that Alice and Bob certainly have differences in taste, but the differences are not that big. And we can also do the same thing with sentences. Here, for example, we have two sentences. Chris loves me more than Linda loves me, and Jane likes me more than Chris loves me. So then we count our words for sentence 1 and sentence 2. And we find that we have 8 dimensions here, 8 different words. So our vectors are S1 and S2. And here again is our cosine similarity function. We do our math just in the very same way that we did previously, only with 8 dimensions instead of just 3. And we end up with an angle of 34.6 degrees, which is very similar to this 36-degree angle. So now we are ready to apply what we have learned about cosine similarity to our music database and to item-based filtering. Here we're seeing our ratings indices, our usernames, and the two bands which we want to compare, namely Phoenix and Passion Pit. If we were doing user-based filtering, we would compare each row against each other row. But since we are going to do item-based filtering, we will actually be comparing the Phoenix column with the Passion Pit column, which also means that we need to pick out the users that have rated both bands at the same time. We are also going to adjust our cosine similarity formula a little bit. So we're going to take here the rating that R that the user U gives to item I, but then in order to compensate for grade inflation, we're going to subtract the average rating that the very same user gave for all the items that she rated. That way we'll be able to compensate a little bit for the grade inflation. And just as we were getting ready to make our calculations for Phoenix and Passion Pit, we get a call from our agent saying first we have to perform the calculations for Kacey Musgraves and Imagine Dragons. So that's what we're going to do here. We see we have 3 ratings for Musgraves, 3 ratings for Imagine Dragons by Ben, Chris, and Tori. And we have also calculated Ben's average rating, Chris's average rating, and Tori's average rating. So now we're ready to apply our modified cosine similarity formula, in which we are calculating the sum of all ratings for Musgraves minus the average multiplied by the ratings for dragons minus the dragon average. All of that divided by the square sum of our Musgraves product and times the square sum of our dragons product. So this leaves us with 4 minus 2.75 times 3 minus 2.75 for Ben, plus 4 minus 3.2 times 4 minus 3.2 for Chris, plus 5 minus 4.25 for Tori, and 4 minus 4.25 for Tori. And then here we have similar calculations for our denominator. This leaves us with a result of 0.5260 as our cosine similarity. And since we know that the cosine of a 60-degree angle is 0.5, we can calculate here that the cosine of a 58-degree angle is about 0.52, close enough to our result, so that we know that the two bands are about at a 52-degree angle. All right, what does the code look like for such item-based filtering? Well, first we have to set up the table in Python. And then we're going to compute the values in a similarity matrix. So we set up a compute similarity class here with the first band, the second band, and the user ratings. And then we are going to calculate the averages. Then we're going to set up our numerator and our first half of the denominator, our second half of the denominator for our cosine similarity formula. And then we're going to set for each user and ratings in our user ratings here, in our users. We're going to calculate the average. We're going to calculate the numerator with this formula. And we're going to calculate the denominator, first part with this formula, and the second part of the denominator with this formula. And then for our result, we're going to return the numerator divided by the square root of denominator 1 times the square root of denominator 2. And that is our cosine similarity formula adjusted by the average. So now that we know how to calculate the cosine similarity between two different items, we can set up a similarity matrix like what you're seeing here. And here is our intersection of Casey Musgraves and Imagine Dragons with our 0.5260. And we can fill in all of these other values here. Once we have a completed similarity matrix, we can use it to predict how a user will rate any of these items in our matrix once we know how he has rated one or more of the items. For this purpose, we will use this formula here. The P stands for the prediction of our user, for example, David, on our item, for example, here, Casey Musgraves. In other words, we're going to calculate using this formula what our prediction is for the rating that David will give Casey Musgraves. The N here is each of the items that David has rated that are similar to Casey Musgraves. The SINN here is the similarity score between I and N that we're going to pick from here, from our similarity matrix. And the RUNN is the rating that David has given item N. Since our similarity scores here are on a scale from -1 to +1, this works best when also our ratings are on a scale from -1 to +1, so we will convert these. So in order to normalize our ratings, we are going to subtract the minimum rating from the actual user rating, which we're going to multiply by 2, and then we're going to subtract from that the minimum from the maximum, and we're going to divide that through the maximum minus the minimum. So for example, if any user rated Fall Out Boy a 2, here's what's going to happen in comparison to David's ratings. We have here the 2 from our formula here. And then we're saying any user rated Fall Out Boy a 2, so we're going to use the rating of 2 minus the rating of 1 that David gave, minus our maximum minus the minimum, divided by the maximum minus the minimum, which gives us -2 in the numerator divided by 4 in the denominator, which gives us a normalized value of -0.5. In order to reverse the normalized rating, we apply the denormalization formula. And as you can see here, we end up with the initial rating. That is the rating of the user who rated Fall Out Boy a 2. So now that we have our similarity matrix filled out, and we have our normalization formula, and we have calculated how the relationship is between Imagine Dragons and Kacey Musgraves and the other users who have rated them, and that we know how David has rated Imagine Dragons, Daft Punk, Lorde, and Fall Out Boy, we can predict how David would rate Kacey Musgraves, and that's what we're going to do. We are now going to use this formula that we already know, and we're going to plug in the values from our similarity matrix, and we're going to multiply them with the normalized values for David's ratings of Imagine Dragon, Daft Punk, Lorde, and Fall Out Boy. And we're going to divide that by our denominator. This, in the end, will give us 0.753. Now we're going to use our denormalization formula that we have encountered previously. And we're going to plug our 0.753 in right here. And that will give us a result of 4.506, which allows us to say that David will rate Kacey Musgraves a 4.506 based on the similarity matrix that we have calculated and based on his normalized ratings for the other bands. But of course, that's a lot of calculating, and why should we do that by hand if we can't have a computer do that for us? This is where the Slope 1 algorithm comes in. Now let's suppose that Amy gave a rating of 3 to PSY and a rating of 4 to Whitney Houston, and Ben gave a rating of 2 to PSY. And now we want to predict how Ben would rate Whitney Houston. So our Slope 1 algorithm, which is weighted, really does exactly what we've done previously with our cosine similarity. Our Slope 1 algorithm works in 2 steps. First, it computes the deviation between each pair of items, which is what we did by hand previously, and then it makes predictions, which is also what we did by hand previously. So let's take another good look at this table. We see that Amy and Ben rated Taylor Swift a 4 for Amy and a 5 for Ben, and rated PSY a 3 for Amy and a 2 for Ben. And then Amy rated Whitney Houston a 4. So our first step is to compute the deviation. In order to understand how Ben would rate Whitney Houston, we need to understand how both Ben and Amy have rated Taylor Swift and PSY, and that's what we're going to use now. We know that we have 2 users, so the card for S, I, and J for X evaluates to 2, which is Ben and Amy. And we are going to now calculate the sum of the user ratings. So our deviation for Taylor Swift and PSY is as follows. We have 4 minus 3 divided by 2 users plus 5 minus 2 again divided by 2 users, which gives us a 2. We're going to note this right here. And then we're going to calculate the reverse as well, which is the deviation of PSY versus Taylor Swift. And now we're going to calculate the 3 minus 4 and the 2 minus 5. Each of them divided by 2, which gives us a minus 2. We're going to fill this in here. We call this table our deviation table. So we use this deviation table so we can make predictions with our weighted Slope 1 algorithm. The formula for this algorithm looks like this. And that may look really scary, but let's step through it. The PWS1 of user with respect to item J is really just our prediction using weighted Slope 1 of our user Ben's rating for item J. So this means our user would be Ben, our item J would be Whitney Houston. And the entire numerator here means that for every musician I that Ben has rated, well, except for Whitney Houston, who he has not rated, we will look up the deviation of Whitney Houston to that musician. And we will add that to Ben's rating for the musician I. We multiply that by the cardinality of the pair, right here. And that's the number of people that rated both musicians. And that is Whitney and musician I. And time to put everything together. We see here our deviation table that we have calculated, and here are Ben's ratings for Taylor Swift and for PSY. So in our numerator here, we know that Ben has rated Taylor Swift and gave her a 5, and that is the UI right here. There. And the deviation of Whitney Houston with respect to Taylor Swift is -1. That is right here. So in other words, this here then evaluates to 4. And there were 2 people, Amy and Daisy, that rated both Taylor Swift and Whitney Houston. Amy and Daisy. So that gives us a 2 for CJ and I, right here, and right here. So which means that this here evaluates to 4 times 2, 4 times 2, 2 and 8. And we know that Ben has rated PSY and gave him a 2. So this means that the deviation of Whitney Houston with respect to PSY is 0.75. And then this 0.75 means that the deviation of J and I plus U with respect to I evaluates to 2.75 for Whitney Houston and PSY. And since we know that 2 people rated Whitney Houston and PSY, namely Amy and Clara, we can now resolve this entire term here to the 2.75 times the 2 users. So that turns into 5.5. And if we sum up steps 5 through 9, then we get 13.5 for the numerator. We remember that our numerator was 13.5. Now let's talk about the denominator here. For the denominator, it's important to understand the cardinalities of our musicians. We know that 2 users have rated both Taylor Swift and Whitney Houston, and we know that Ben himself has rated Taylor Swift and 1 more musician. So that makes Ben's cardinality 2, and it makes Whitney Houston and Taylor Swift's cardinality 2 as well. So if we sum those up, we get 2 plus 2 equaling 4. So we plug that in here, and we have 13.5 divided by 4, which means that our prediction of how well Ben will like Whitney Houston is the result of that division, which is 3.375. And that works great when we have a handful of users and a handful of artists. But what if we have our streaming music site, again with millions of users that rate 200,000 artists? And that is where the beauty of the Slope 1 algorithm comes in. I do not have to rerun the algorithm every single time I get a new user who supplies a new artist rating. All I have to do is to keep in memory the deviation table that we have generated for the total number of people rating whichever items we are interested in comparing. Take a look at this example below. What does all of this look like in Python? Well, first we start with our user table, of course. Then we want to calculate our deviations and set up our deviation table. And here's how this looks in pseudocode. So for each person in the data, here we want to get their ratings. And for each item and rating in that set of ratings, we want to compare that with each item 2 and rating 2 in that set of ratings. And then we want to add the difference between the ratings to our computation, and that sets up our deviation table. So in step 1 of our slope 1 algorithm, we are going to use the self.data dictionary and the values method, which extracts only the values from the dictionary. So in other words, the first time that we loop through our user set here, we are going to extract the values Taylor Swift 4, Psy 3, Whitney Houston 4. So now that we've looped through our user data set, we're going to add these next 3 lines of code plus our 1 comment, and we're going to say that we are using the self.frequencies and the self.deviations libraries or dictionaries here with the setDefault method, and we're going to initialize these here, these settings. And setDefault takes 2 arguments, a key and an initial value. And if we don't have the key in the dictionary, it is added to the dictionary with the initial value. And now we're ready to add our next rows of code here, and that is a for loop in which we compute the difference between the 2 ratings, and we add that to the self.deviations and the running sum. So in other words, what we're doing is we are using in the outer loop here, we get our ratings, Taylor Swift rating 4, and in the inner loop, we're looking at item number 2, for example, PSY, and the rating 2, and that is then 3. And the last line of our code here adds the 1 to the self.deviations, which is Taylor Swift and PSY. In step 4, now that we have identified our item, we have identified our item 2, we have set up our deviation table, and we know the frequencies that we're calculating right here. We can now finally loop through our deviation table and then set up this equation by saying we're taking the ratings for item 2 and we're going to divide them by the self.frequencies for item 1 and item 2. And that is our denominator. And now we're ready to test our code. So we are going to call the recommender method with our users2 table, and we're using our compute deviations method in order to show us our deviations. And here is our deviations table for Taylor Swift, Whitney Houston, and PSY. If you would like to read a more detailed analysis of the code that I've just discussed, please go to Chapter 3 of Zakarsky's Programmer's Guide to Data Mining and look at the PDF and at the recommender3.python file. So thanks for watching this video on complex item-based recommender systems, and I wish you much fun on your journey through data mining.